Thank you, Cathy, for accepting my invitation to discuss some aspects of education in neuroscience. As you know, my aim is to create awareness about this innovative topic locally, so I would like to discuss particular aspects of education in neuroscience with you. Recently, just have finished writing a book called Education Neuroscience, The Basics, which is soon to be published. So I want to start off by asking you to tell us more about your new book that you have co-authored with Professor Michael Thomas. What exactly is its focus?
Okay, well, thanks very much for having me, first of all. Really happy to be here talking to you about educational neuroscience. And the book is part of a series called The Basics. So they are sort of introductory guides to different topics, many of which are kind of new areas of research. So the book is called Educational Neuroscience, The Basics, and it's coming out in October of this year, published by Routledge in the UK. And it's what it says on the tin. You know, it's an introduction to those who haven't come across the idea of educational neuroscience, about what this new interdisciplinary field is all about. So it's aimed at those interested in the connection between brain sciences and pedagogy, teachers, and really anyone who has an interest in how learning works in the brain.
The sciences of mind and brain are revealing a lot of really useful ideas for improving education. What ideas are these?
Wow, it's a big question. And the first thing I'd say, just as a way of sort of scene setting, is that most things, almost everything that teachers already do works. Like, educational neuroscience isn't about saying we need to completely rethink everything that teachers are doing, because over many decades and centuries, teachers have built up a huge amount of understanding about what works in the classroom through trial and error. I think that what educational neuroscience and the sciences of mind and brain, like the whole, because it's a new area, it has lots of different names. It's more about understanding how things work a bit more precisely, so that you might be able to work them better. And there's an analogy that we use in the book, which is from the medical field, because there's lots of parallels we make with changes that have happened in the introduction of a more scientific approach to medicine, to what we see as the introduction of a more scientific approach to education. And the medical example is, it's been known for centuries that chewing the bark from a cinchona tree can help ward off malaria, right? So that's a piece of ancient knowledge. It was found by presumably chewing lots of different kinds of bark, but finding that was one that worked. But then what we've done, through understanding the mechanisms by which that preventive piece of medicine actually operates, we can then really fine tune it. So now you don't have to chew bark. You can take pills on a very scheduled dose, which don't have side effects, which are that can be kind of like bespoke to the individual, to different conditions. And it's a bit like, you know, I think there's a parallel there with education. So it's not like we're saying, oh my God, we need to throw everything out and start again. It's more about those kind of fine-tuning things. And I think there's an example that might be useful as well, that kind of frames why this kind of thinking is important, because a lot of pedagogy has been based on psychology, essentially, like looking at how behavior works from the outside in rather than from the inside of the brain out. And sometimes things that you see on the outside, you assume the way that they're working inside, but you might not be right. So an example of this is there's a project that is a research project that's still ongoing here in the UK called Unlock, which is looking at how the brain deals with counterintuitive facts in science and maths. So in science and maths, you encounter lots of things that are actually different from what your experience has told you they are. So a simple example is, we go out every day from when we can walk, and we feel that the world is flat. We don't fall off the edge, we don't see an edge, it doesn't seem round. And then we go into a science class and we learn that actually the world is round, that we're living on a spherical object. And what we used to think was that when you learn this new piece of knowledge, the old knowledge that the earth is flat just somehow disappears from the brain. It's not there anymore. But in fact, that knowledge still remains in the brain. And it's more the case that what you need to do is you need to deploy another part of the brain, what's called kind of an inhibitory process in the brain that tells the old knowledge, hush up, you know, that kind of reminds it, no, we're not in a flat world anymore. We've got this new knowledge and we need to point our attention over there. So that's just a small example of how something we thought worked in one way actually works in a slightly different way. And I'll stop talking. I do have a tendency never to put a full stop. So do put some full stops in for me. I'll put one in there.
No, very interesting. If you had to give a short talk with educators and parents as your audience on the most vital parts of the brain, can you explain what they are briefly and their functions?
So I hope this doesn't sound like a cop-out, but I wouldn't really do an anatomical tour of the brain in that way. I think that how we used to think of the brain is in these very modular units. You know, the hippocampus does memory and the limbic system does emotions. But as we understand more about how it works, the idea that this part does this function isn't the most useful for understanding how things work, because it's much more about systems and their connections. So what I would instead talk about are, what are the priorities for the brain? And by priorities, I'm really talking about the things that the brain has developed to do through its evolutionary history, which is, you know, that's what it is. It's an evolutionary organ. And what those priorities are firstly dealing with senses and movement. That's the fundamental basis of, like, about 80% of what goes on of like the brain's real estate is concerned with processing senses and generating a motor response. And that might make us think about very primitive things, but actually that also applies to very sophisticated things that we do. And all learning is built on those sensory motor systems. And then the next up on the list of priorities are the emotions. So dealing with kind of our emotional engagement with the world. Then moving up, we have, very connected with the emotions, and something that's pretty hard for the brain is dealing with other people, so social cognition. And then last of all is kind of thinking and learning. And the reason that I think that's important is because I think often in education we act as if thinking and learning is what the brain naturally does, because we know that from seeing how babies and toddlers develop, that we learn and we're curious and we adapt and we take on new information. But that kind of learning and thinking is very different from what we ask the brain to do in the classroom. And I think we often forget what it's actually built on. So I would kind of give my brain tour in terms of those priorities. And I would also talk about, I think one thing, if there's one thing that I'd say we've really underestimated in education, it's motivation. And I think that any teacher knows the difference between teaching a motivated child and an unmotivated child is black and white. You know, in one, your job is simple and flows and is creative, can go in a million different directions. And if the child's unmotivated, it's a battle, it's a struggle for learner and teacher. And I think that is huge. I think that is, you know, if we think about how children naturally are, and even think of a child who supposedly has attention problems, you could watch that same child playing Minecraft for hours on end, where they might be engaged, they might be being creative, they're learning, they might hit a bit of a barrier, but then they'll go off and do their own exploratory learning because that's what they need to get to the next stage. They'll take new learning on board and then they'll move on. But that same child might be staring out the window in an English class learning next to nothing. And the difference between those two is motivation. Like, that is all. And so I think that in education we often see it's a bit of an add-on, but actually I think when we go back to what the brain gets excited by, if you like, then it's absolutely fundamental to learning.
I think novelty is a very important aspect in teaching and learning.
Yes, I'd agree.
Part of it, you know?
Yeah, I mean, I think if you think about younger children, novelty is the fuel, isn't it? Novelty is the fuel for learning, because our brains are pieces of predictive machinery. You know, our brains like to make things automatic, but if something's new, it doesn't fit into an automatic program. So it's like it's like red flag to the brain. It's like, wow, here's something that I need to deal with in a new way.
And the students get more engaged when there's novelty, you know,
Definitely.
automatically.
Yes, or absolutely automatically, because they can't run on autopilot because there's no program for it yet, because it's new. Yeah,
exactly. What connection is there between brain development and teaching and learning? And what does it mean for teaching? Why is this so crucial?
So I think there's different ways of answering this question. I think there's one way of answering it, which is to do with the different stages of the development of an individual child's brain. Because we do know that there are things that happen over developmental time, typically, you know, so there are certain things like emotional regulation, which follow obviously there's a lot of individual differences, but follow some kind of developmental pathway, or the development of executive functions that follow a developmental pathway. But I think there's another way of thinking about development, which is more to do with understanding the evolutionary development of the brain, which is more what I was kind of alluding to before, and the fact that the brain didn't evolve to be taught in a classroom. And often what we're asking the brain to do in the classroom is take parts of the brain which were sort of shaped by evolution to do certain things, and we're asking them to do something else. I'll explain it with an example, because I know that might sound a little bit esoteric. But the point of it is that if you're taking something which has evolved to do one thing and you're using it for another purpose, then it might not work perfectly for that job. Like if you're trying to dig a hole in your garden and the only thing you have to hand is a screwdriver rather than a spade, you'll be able to dig a bit of a hole, but it's not going to be the best hole you could possibly dig, right? So I think that that's something that is important in the classroom, because I think there's assumptions that we make that are sometimes wrong. So if we think of the example, so as children, like very young babies and toddlers grow and experience the world, one thing that they learn pretty early on is that an object is the same object whichever way up it is. It's called the invariance principle. So if you hold a cup the right way up and you hold it upside down, the child, through various complicated processes in the visual cortex, understand that that object is still the same object, no matter what its orientation is. So whether the cup is on the handle's on the right or the left, or whichever way up it is. And that's an important thing for processing the world, because you don't want to process what is the same object in a lot of different ways, or it's almost like an infinite number of possibilities. But then we put those children in the classroom, and in English at least, they meet certain letters, like they meet the letter P and the letter B, or the number 6 and the number 9. And their brain has, through its evolutionary, the sort of flexibility that it's evolved evolutionarily, has come to understand that an object is an object whichever way round it is. So it's not that they get confused between B and D or P and Q because they look a bit similar. It's actually it's deeper than that, if you like. They've learned that objects can be seen from any orientation and they're still the same object. So actually differentiating between them is a real piece of unlearning that they have to do in the classroom. So that's just a really small example of something where we might assume certain things about development that if we actually understand how the brain is doing development, we might see slightly differently. Like we might spend much more time on differentiating those letters, be much more explicit about the fact they break the normal rules of a cup being a cup.